For question 3 of the midterm 2 solutions, we have the question asking that the surface of a sphere has a potential given by V of r theta, where r is the radius of our sphere, is equal to k naught p naught cosine of theta plus k3 p3 cosine of theta. So right away we know that because it's the potential, we have k naught and k3 with the correct units to make this work, and our p naught and p3 are Legendre polynomials of the 0th order, the 3rd order of cosine theta. So question A, or part A, asks, what can we say about the charge density rho of r, theta, and phi inside and outside of the sphere? And in the problem it says that Laplace's equation holds inside and outside. So right away we know that from Poisson's equation, the Laplacian of our potential is a negative rho over epsilon naught, I believe. And this turns into Laplace's equation when rho is equal to 0. So if we have Laplace's equation holding inside and outside the sphere, that means that the charge density rho must be 0 inside and outside the sphere in order for Laplace's equation to have this form. So rho is equal to 0 for inside and outside. So that's part A. So part A is pretty straightforward. Just remembering the fact that Laplace's equation holds means that the charge density from Poisson's equation is 0. Part B asks us to find the general form of the solution inside the sphere for the solution V of r and theta, and then it asks you to evaluate that at a certain point. So we want to find V of r over 2 and pi of our sphere. So right away we can see that this is inside of the sphere because the radius, the point at which we're evaluating the radius, is r over 2, which means that it's at a position r that's inside of that spherical surface. Anything that has r greater than 1 or r greater than r, that will mean that we're outside of the sphere, but because r over 2 is less than r, we are inside the sphere, which means that we can take our general form of the potential for inside the sphere, which is the sum over all of L of a sub L r to the power of L PL cosine of theta, where again this is just a general form of the potential in spherical coordinates inside of a sphere, with a sub L being our coefficient, r to the power of L, and PL is a Legendre polynomial, and it's a sum over all terms of L. So if we write out what is our initial potential at the surface, we have V of r theta is equal to k naught p naught cosine of theta plus k3 p3 cosine of theta. And now we can write out essentially this general expression, including the exact same L terms. So we have V of r is equal to r theta is equal to a sub 0 r is equal to r to the 0 p0 cosine of theta plus a sub 3 of r is equal to r cubed p3 cosine of theta. And now essentially we just have to compare these two, because this is the general form of the potential that we have for a sphere inside of it, and this is what we're given as our boundary conditions. So we know that our general form on the boundary should be equal to what we've been given in the problem. So we can essentially just look and compare between these two terms because they must be equal. So in this initial term, p naught and p naught are the same. This r equals r to the power of 0 term goes to 1, sorry. So we just have that a naught is equal to k naught. Similarly over here we have that a3 is given by k sub 3, but now we have this r cubed term, where again it's big capital R because we're evaluating this at the surface, r is equal to r. So we now have our general expression inside the sphere where we have V of r of theta is equal to, I'm going to draw a line here so we don't get confused, V of r theta is equal to a naught p naught cosine of theta plus a3 r cubed p3 cosine of theta, where now this is a little r because I'm just expanding this expression to account for the r little r is equal to 3 term, And then when we evaluate this at our position r over 2 and pi, we have v r over 2 and pi gives us a naught. Of course, our p naught value is always going to be 1 for the Legendre polynomial, so we just have a naught plus a3 r over 2 cubed, and then p3 of cosine of pi, which is just negative 1. We can now substitute in our values for a naught, so we have a naught is k naught, plus a3 is k3 over 8 r cubed in the numerator. And essentially this p3 is negative 1. I will see I have a little bit of space here, so I'll fill that in quickly. The way I remember this is I just remember the general form of a Legendre polynomial of x, so p3 of x is simply 1 over 2 5x cubed minus 3x, and you can remember this from the Rodriguez formula. So I just remember it in this form instead of in the cosine theta form because I think this is a little bit easier to remember. So we substitute negative 1 because in this case our x is just negative 1. Then we have negative 5 plus 3 is negative 2, so we end up with negative 2 over 2, which is just negative 1. And this would be x is equal to negative 1. So that means that p3 of negative 1 is simply negative 1. And this is v of r over 2 and pi. And so finally, our potential that we find at r over 2 and pi inside the sphere is k naught minus k3 over 8. So this could be potentially confusing in some sections, so I will kind of try to explain again what my logic was. So we start off with given, this is the potential on the spherical boundary on the surface of the sphere, which we can tell that's at the surface because we're at r is equal to big R, which is the radius, at any position theta. So we can be anywhere on the sphere, we can rotate the sphere, and we're always going to be on the boundary and have this potential. It's k naught, p naught, cosine theta plus k3, p3 cosine theta, which p naught and p3 are just our Legendre polynomials in our spherical coordinates. Part A was asking what is the charge density inside and outside the sphere, which we know is just 0 because Laplace's equation holds. And then for part B, we want to find the potential at some position r over 2 and pi. So we can initially start by finding the general solution in our spherical coordinates for our potential, which is just dependent on r and theta. And again, we start inside of the sphere because we have that r over 2 is less than our radius big R. This is just our general form of Legendre polynomials. We know this is what the potential is on the boundary, so then we can solve this this general expression of v of r of theta at the boundary, and then from that we can get what is our coefficient a naught and our coefficient a3. We can then plug in our general expression and use those values of a naught and a3 in order to expand through, and then we simply have to evaluate our general expression of our potential at our position that we're looking for of r over 2 and pi. And one more potentially confusing area is this Legendre polynomial p3 of cosine theta. So what I did was I took our value of pi, so theta is equal to pi, I plugged that into the cosine theta term. Cosine of pi is negative 1. So we end up with just an expression for the third Legendre polynomial. I guess it's the fourth because we start at p0, so the fourth Legendre polynomial evaluated at negative 1. And I like to remember the Legendre polynomials in terms of x's and not cosines because I think that's a little bit easier to do. So then I recalled that this is just the general form of p3. That's 1/2 5x cubed minus 3x. Again, you can always derive this from the Rodriguez formula, which you might have to remember, or it could be given on a formula sheet. Then I just substitute x is equal to negative 1, which is what I had for my p3 term, which gives negative 1 to the power of 3 is negative 1, multiplied by 5 is negative 5. Negative 3 times negative 1 is positive 3, so negative 5 plus 3 is negative 2. Negative 2 divided by 2 is negative 1. So our evaluation of p3 at x is equal to negative 1 just gives us negative 1. And that allows us to plug that value into our Legendre polynomial, our fourth Legendre polynomial p3. And then simply have to plug in a naught, plug in a3, expand this r over 2 cubed term, and do some cancellation. Cancel r cubed and r cubed. And we end up with the final potential at the position r over 2 and pi is equal to k naught minus k3 over 8. Now this is quite a challenging problem. As you can see, there's quite a bit of work we had to do. But to make it simpler, you always want to start with recalling what is the general form of the potential inside or outside the sphere. In part C, we ask for the similar setup, but outside the sphere. And the way I always think about it is always kind of a matching problem. I want to know what the general form is at the boundary, and I'm given what I know the potential is at that same boundary, so I can just simply match up coefficients in order to make them equal, and I can then solve through, get the general form. Given that I know these coefficients, I don't have to solve for them because they're just given to me by the boundary conditions, and I can plug in the value that I want to find. Part C of question 3 asks us to find the potential at some position V is 4r and 0. So again, we have our general solution where we have V of little r and theta. And this position here now, because 4r is greater than r, we are going to be outside of the sphere, which means that our general solution to the potential in spherical coordinates becomes now our coefficients b sub l, 1 over r to the l plus 1, and again our Legendre polynomial pl of cosine of theta. So similar to part B, I'm going to start by writing out this general form expanded at the position little r is equal to r, and our general theta, which is simply just going to be b0, 1 over big R to the 1, because 0 plus 1, p0 cosine of theta, plus b3, now it's going to be 1 over big R to the 4, again it's 3 plus 1, p3 cosine of theta. So it's the same steps as in part B, but now we're looking at the region outside of the sphere. So again, we have our general solution to our potential outside of the sphere, and looking at what our boundary conditions are, we can only include the L is equal to 0 and L is equal to 3 terms. So V of R and theta is equal to K naught, P naught cosine of theta, plus K3, P3 cosine of theta. And once again, now we simply have a matching problem on the boundary. So right away we can look here and we can see that B naught is equal to K naught times R, given the matching of the coefficients here, because P naught and P naught are the same. And over here we have that B3 is K3 times R to the 4. Because if I were to substitute that into here, that would give me K3 at the boundary. So we know that the general form is V of R of theta is now going to be B naught 1 over R, P naught cosine of theta, plus B3 1 over R to the 4th, P to the 3 cosine of theta. Where we now know what B naught and B3 are, we're looking at the specific point 4R and theta is equal to 0. So that gives us B naught, again P naught is always 1, so it's B naught over 1 over 4R plus B3 1 over 4R to the 4th, and then P3 of cosine of theta would just be P3 of 1. Again, because cosine of theta, cosine of 0 is 1. And right away, again, I can remember from what we did in part B, where P3 of x is 1/2 5x cubed minus 3x. And when x is equal to 1, this is just going to be equal to positive 1. And you can check that at home. So again, this is the step that you might have some trouble remembering on a test, but it's just given by the Rodriguez formula in order to find what is the fourth Legendre polynomial P3. And I always like to look at it in terms of x's instead of cosines, because I find that a little bit more intuitive to understand. So now we can simply continue and expand this through. So we have V of 4R and 0 is equal to B naught, substituting in just gives me K naught times R over 4R, plus, substituting all these terms in, I have B3, which is K3, sorry, this is not R sub 4, it's R to the power of 4, K3 R to the 4th divided by 4 to the 4th, R to the 4th times 1, because P3 of 1 is just 1. And our final potential at the position 4R and 0 is just equal to K naught over 4 plus K3 over 256, since this R and that R cancel, and that R to the 4 and that R to the 4 cancel. So to summarize what we have, so very similar to part B, except now we're outside of the sphere, so we have to look at the general solution to Laplace's equation in spherical coordinates in terms of our coefficient B sub L, 1 over R to the L plus 1, and our Legendre polynomial in terms of cosine. 4r is greater than r, and that's what makes us know that we're outside of the sphere. We can use our boundary condition in order to set what we know for b0 and b3, where again this mistake here is actually should be r to the 4th, which comes from this denominator here. Then we know the general form, given that we have now the coefficients b0 and b3, and then we can just plug in our value of little r is equal to 4r and theta is equal to 0, again with our p3 of 1 is equal to 1. And then this was kind of the same format and same general steps to the solution as we saw in part B. So that's kind of how you want to approach these problems always, is you know the boundary condition, you know what the general form is, you can solve for that general form at the boundary, find your coefficients just by matching, and then you know now what the general form is given that you have the coefficients, and you can plug in the position that you're looking for. Part D, I'll just tuck that in here quickly in this video because it's quite straightforward. It says what happens when r, like little r, so this little r here, or in the general expression here, becomes much, much greater than big R. And in that case, if we look at our general form, which is what we have in this equation here, we see that we have a 1 over little r to the power of 4 term. Now, if we are much, much greater than the big radius, big R, this term here is going to fall off quadratically, which is our octupole term, because we have 1 over r to the 4. And what that means is that this term here essentially is going to go to 0 much, much faster than this monopole term here, where we have just a factor of 1 over little r. So if we're at a distance much, much further away than the radius of the sphere, where little r is much, much greater than big R, this octupole term here is going to go to 0. It's going to be negligible. And this term here, this monopole term, is what's going to dominate. So we're going to end up with the potential acting like a monopole. So we're going to have our normal Q over R expression, or 4 pi epsilon naught expression, just like our normal monopole, where here our Q will be 4 pi epsilon naught K naught R, given that we have that is our coefficient of B naught. So for part D, at some position much, much further away than the radius of the sphere, little r is much, much greater than big R, we're going to have our potential acting like a monopole.